Okay, good afternoon, everyone. Welcome to the November 2020 edition of the VLab Forum. We continue with our totally virtual format from wherever you are out there in the grand VLab land. Welcome this afternoon. We are very lucky to have an interesting topic about the National Blend of Models. Reminder, the VLab Forum, it's designed to look at different types of projects that are either possibly transitioning to weather service operations or on their way into weather service operations, in some cases already in weather service operations, which is the case with the National Blend of Models, but we are going to focus on a specific aspect of that. A reminder of our format, we'll have about 30 minutes or so of content provided by our speakers and then a Q&A session which will follow. We ask that you keep your questions for the Q&A session unless it's something really urgent and clarifying in nature. This is designed to be sort of collegial, so we really welcome all types of questions, and if you don't get your question asked or you feel more comfortable asking it offline, the speakers, of course, will be available to dialogue with you further after the seminar. Another reminder, the session is being recorded, and John Chattel, who is our technical logistic program manager, will upload the recording of this up to the VLab Forum website shortly after the conclusion, and you can share it with your colleagues or watch it again if you wish. So today we are going to be talking, as I already said, about the National Blend of Models, which is a flagship guidance that is impacting virtually every aspect of weather service operations. It is the basis for the collaborative forecast processes, one of which is the QPF collaborative forecast process demonstration coming up that Weather Service is planning. One of the trickier aspects of the blend is handling tropical cyclones and accurately depicting them and forecasting them. And that's what we're going to learn about today. So our speakers are Geoff Wagner of CIRA and Samantha Camposano of ACE Info, both of the Meteorological Development Lab. So sit back, relax, and I'm going to hand it off to Geoff and Samantha. Take it away.
All right, great. Thank you, Steve. Can everybody hear me okay? Okay. All right. So we're going to be talking about using feature-based methods to improve the tropical cyclone forecast that you'll see in the National Blend of Models. Before I get into the how, let's talk a little bit about why we're going down this road. Our motivation here is to better incorporate direct model output, that's the numerical weather prediction, from hurricane model, and the official tropical cyclone forecast message, also called the WTCM, product from the National Hurricane Center into the National Blend of Models, specifically in the wind speed forecast. Now, some things that we really specifically want to aim for are, we want to avoid washing out wind speed magnitudes. We want to leverage all the information we have from these inputs to create a single coherent forecast feature that we're going to place back down on the NBM forecast background. And we also want to maintain the integrity of the official NHC forecast, the TCM, whenever available. So what do we mean by that? Using whole grid-based techniques, so this is mean absolute error weighting or expert weighting of input forecasts, can create some odd features forecasts for high magnitude events such as tropical cyclones. So if you look on the images on the left, the far left one is the NBM 4.0 tropical wind speed forecast, which incorporates the HWRF, HMON, WTCM. The one on the right is the 10-meter wind speed, which does not incorporate those. You'll notice that the magnitudes of the blended models can tend to get washed out. So in the far left side, you'll see the characteristic concentric circles from the WTCM forecast on the top side of the image, but you've got a lower magnitude kind of secondary looking cyclone complete with another eye to the south of it. Additionally, on the right, you've got really no cyclone that's discernible at all. So you can run into all sorts of these problems, like multiple eyes, a broadened wind field, or you might not even catch the cyclone at all in your forecast. Likewise, diverging forecast solutions can present problems. So for example, here, once again, this is the NBM 4.0 tropical wind speed. You can see where, due to the timing of availability, you've got some disagreement between the NWP and the WTCM forecast. And you almost look like you're forecasting a whole second cyclone to develop and shoot off of the first one. Needless to say, this is a problematic forecast. So enter feature-based techniques, which are also sometimes referred to as object-based. They're not new. In fact, tools exist out there right now to perform tasks like verification using these methods, like the Model Evaluation Toolkit's Node tool. And what they do is they let you take a feature of interest from a whole domain forecast and treat it individually. So by applying this concept to blending forecast inputs, we can combine the representation of the TC from various models by combining them over their respective centers, which really helps to preserve the magnitude. Additionally, these hybrid features that we've created can be placed back on the background forecast, in our case, the National Blended Model's wind speed, at an agreed upon location. So to clarify a little bit about what this technique is and is not, we are a collection of simple techniques to apply feature-based concepts to blending forecasts from multiple input models. We are not a physical, dynamical, or statistical model, and we don't really look at this underlying structure of the TCs from the models as we combine them. We are an algorithm that makes decisions on combining features of interest based on empirically decided thresholds and fuzzy logic, which is just non-binary or allowing for degrees of truth that we add in for matching. We are not a machine learning technique, although there is certainly opportunity to apply machine learning concepts to individual steps of it, such as classification, identification, and matching. So where does that leave us? We're a specialized tool that addresses the requirements of the NDM and allows us to apply a specific set of rules to preserve the WTCM forecast when it's available. So if you visually break down what we're doing, it's pretty simple. It looks roughly like this. Your first step, you want to identify the cyclone features in each of your input models. Then you take those features that you've identified and you combine them by matching them across models and then stacking them into a single hybrid feature. And then finally, we place that back down onto the background forecast, also allowing for us to do a few things like smoothing along the edges of the forecast and removing any conflicting background features. When you add in some of the intermediate logic, it breaks down to about 5 steps. The first of those is to identify features. And the first question you have to ask when you're doing that is, what is a feature? What do I care about in this forecast? And what we've settled on for identifying features in both the DMO and in the WTCM is about 14 meters per second, which equates to around 31 miles per hour, which is roughly wind advisory criteria. We also, for the WTCM, have a kind of secondary threshold of 17.5-ish meters per second, which corresponds to 34 knots. And we care a lot about what we do with winds that are greater than that speed from the TCM forecast. So to show you how this works, it helps to walk through a case study. And this was our kind of prototypical case that we set up as we were building out this method. It's good because it has multiple cyclones, but not so many that it becomes confusing. And what you're looking at is a 5-day outlook for the Central Pacific for tropical storms Eric and Flossie as they're moving in the vicinity of Hawaii. You can clearly see Eric on the left and Flossie on the right. If we take the DMO from initialized roughly at the time of that analysis and just arbitrarily pick a 30-hour lead time, here you see the wind speed and the mean sea level pressure fields from both the HMON, which is on the top, and the HWRF that's on the bottom. And again, the wind speed is on the left, the pressure is on the right. Nothing particularly troubling about this, but you can see really well the representations of the storms in each model. if we apply our threshold and trace out our discrete features to the HMON, you can see we get very neat and tidy 2 features. You've got Eric on the left, Flossie on the right. But when we take that same method and apply it to the HWRF, it's not quite as neat and tidy. We end up with 5 features, 3 of which are clearly, to the human eye, associated with Eric, and 2 of which are associated with Flossie. So at this point, we're going to want to do a little bit of adjustment to our features before we feed it into our matching algorithm. Primarily, what we care about doing is combining nearby features to reduce the noise that we feed into the algorithm, although some of the individual level of detail is helpful in the larger features. And that creates features that are actually part of the same meteorological feature as a human would see it. We also fill in gaps that are completely internal to a feature, such as the eye. So the goal here is that once we've completed this step, a feature as defined by the code is, what we call a meteorological feature, or a tropical cyclone in this case. From this point on, we operate on the features on their own subgrid, which is just a snip of the larger grid at the same resolution. But we've essentially pulled them off the larger domain grid. I should also note that at this point, we collect a few basic statistics about each feature, such as location and size, that we're going to use when we go to our matching algorithm. So here we have that same HWRF identification step, but when we use our combining algorithm, we've now narrowed it down to 2 distinct features that do have a few smaller features that are associated with a larger scale feature. Looking at each storm individually, these are now on the feature scale subgrid. So you've got Tropical Storm Flossie here. On the top, we have the HMON and the HMON forecast. On the bottom, we have the HWRF. On the left is what we call the feature mask. And this is just a binary field, 0 or 1, telling us where we have identified a feature and where we haven't. And we've marked with a red dot on that map where the central minimum pressure is. And this is very important because this is the point that we stack everything on. And on the right, you can see the wind speed associated with each feature that is masked out by the feature mask on the left. And we did the same thing for Tropical Storm Eric. So everything looks good here. So far, so good. Now we're ready to match. So we have a list of features associated with each model forecast, HMON, HWRF. The next step is to iterate over that list of features for each input model. And we want to calculate a match score between it and each feature in the other models. In this case, we're using 2 models, but when we run with WTCM, we would actually have 3. Match scores are an overall score. It's the mean, a weighted mean of 3 component scores, which are just the normalized difference between the features being compared in 3 logical criteria. The first of those is distance, which when mean sea level pressure is available, we use the minimum central pressure to identify that. For the TCM, which doesn't have a pressure field, we have to find the minimum central wind speed. We also look at size and magnitude, the size being just a head count of grid points that are in the feature, and magnitude, right now we're using a mean wind speed within the feature area. I should note distance gets a double weight in this case. This is something that we actually gleaned from the mode tool documentation, and location does tend to be the best indicator of a match from what we've seen so far. So the component scores are normalized by the largest error value to reduce the influence from scale units. It neatly reduces everything to a scale of 0 to 1. In this case, scores near 0 are the least difference and indicate the best match. So once we come up with this weighted component score, we're ready to do matching. So visually, this is what we want to do. We want to say, okay, we've got our HMON on the left here, we've got our HWRF on the right, and we want to just say, hey, these are the same. Feature 2 in the HMON is feature 2 in the HWRF. I have some backup slides for this if we want to go into more depth in the Q&A, but for now, based on the criteria above, we can just denote that this is indeed what we found and how things were matched. All right, I'm going to pass it off to Sam to talk about the last couple of steps.
Thanks, Geoff. So we have identified our features, we've made our feature adjustments, we've matched our features, and now we're ready to build hybrid features. So now that we've matched, we've determined our match score and our best match for each feature, we have all the information we need to build our hybrid feature, which are the single features that combine the various model inputs for a specific TC and what we'll be placing back on the background forecast. The first step that we need to take is to collapse all the information into a single table so we can determine the total number of hybrid features to generate and specify which TC features from each model to use in each hybrid. Our current method constrains the number of hybrid features to the number of features present in the model with the least total features. Typically, in our experience running this, it's been the WTCM that has had the least common denominator. And the intent of this is to just generate hybrid features where we're likely to have very solid agreement across all input models. So we can show you this pretty visually with a sample table. On the top, we have 3 columns, model 1, 2, and 3. And we have 4 rows of features. So we theoretically say we have 3 models, with model 1 resolving 2 features, model 2 resolving 3 features, and model 3 resolving 4 features. So taking a look at just a pretty binary, red is not a good match and blue is a good match, we can create 2 hybrid features because model 1, 2, and 3 match best with feature 1 across all of those models. And feature 2 across all 3 of those models match best with feature 2 in model 1, feature 2 in model 2, and feature 4 in model 3. So again, this is a least common denominator issue that we find pretty helpful to make our hybrid features. So now that we have that information, we know how many hybrid features we're going to make, we can begin combining the features. We do this with a number of steps. We have to define first a new grid space for each hybrid feature that's large enough to contain the input TC features from each model when they are stacked on the center points that is found when we go ahead and find either that central minimum wind or that central minimum pressure. The hybrid feature grid is, again, just a subgrid, a snip of that full domain at the same resolution. So we're still taking those input features off those like feature domains and creating a hybrid grid space. It's not full domain size. We then after we stack, we're able to build our hybrid feature mask to determine exactly where and how much overlap we have in between those TC features. After we've stacked and created our mask, we can then calculate the final hybrid wind speed feature grid and location. So we can explain this again pretty visually. It's really nice. On the left, we have a theoretical feature 1, and on the right, we have a feature 2. So the area of this feature is 16, feature 1 is 16 grid points, 4 up, 4 across. Center location was resolved at 3, 2, and we have the center on the map, just the big grid domain space, as 1867-15, which is where, in this case, will be relevant with how to resolve where to put this feature back on the grid. And feature 2 is a much smaller feature, a hybrid grid space area of 9. I'm sorry, a feature grid space area of 9, with the center location at 2, 2. So each red dot is a feature. The red dot is the center. A red square is where we found a feature grid point of winds greater than 14 meters per second in our criteria. So we can create a hybrid grid space. Since the feature 2 is smaller than feature 1, we create a space that covers the combined area of both of these features, extending from that center point. So in this case, all of feature 2 can fit on that subgrid of feature 1. So only feature 2 needs an adjustment around those edges to make it the same size, and feature 1 will translate directly on the hybrid grid space. Then we can stack them by the center now that these 2 features are the same size. So we stack them based on that center point. So on the left, we have feature 1 mask. In the center, we have feature 2 mask. And on the right-hand side is our hybrid mask, stacked on that center point. And you can see denoted by the red squares where there is a feature agreement. And the darker red is where both of those models resolve a feature. So to create the hybrid wind speed, now that we've created our hybrid mask, we can now calculate the hybrid wind speed. And so we go about this one of two ways, depending on what we have as data inputs. So when the WTCM is present, the mean speed calculated at each grid point based on the number of input models is what we start with. And then we cap all the values at a maximum of 33, just under 34 knots, so 33.9 knots. And then we place the WTCM data values greater than 33.9 knots back on top. We smooth the boundaries then at differing numbers of features, where we have a feature mask that agrees on from 1 to 2 feature grid points, and then 2 to 3. And then we run another check on the non-WTCM values that are greater than 33.9 knots, and then we reassert those WTCM values greater than 33.9 knots, just to preserve that integrity of the NHC forecast. That's really important. But when WTCM is not present, we calculate the mean speed at each grid point based on the input models. And then we smooth boundaries between the number of differing features masks on that hybrid mask. So we can go back to our Eric and Flossie case. On the left, we have the HMON wind speed and hybrid and feature mask. In the center, HWRF wind speed and feature mask. And on the right-hand side, you can see that where we stacked those two features on top of each other at that center point, on the bottom is our hybrid feature mask, where you can see exactly where there is double agreement on where there is a hybrid feature. And so up top, you can see what that hybrid feature looks like of the mean of those values, where there is that agreement in the hybrid feature mask. Similarly with Tropical Storm Eric, HMON on the left, HWRF in the center, both have center points that become stacked on top of each other, and their data inputs are averaged at those overlapping feature mask, where feature mask equals 2. And it creates a really nice hybrid, a hybrid TC feature there. So here's an example of what happens when we have a WTCM forecast. This is a recent example from Tropical Storm Eta, when it was lingering off the coast of Florida a week ago, maybe. WTCM is on the left-hand side. It's really small on my screen, but there are center points on those hybrid feature, on those feature masks. And likewise, HWRF and HMON. So all three of those features get stacked on those center points that are found. And those winds are all blended together, averaged together, with the WTCM after that fact reasserted on top of those values, preserved entirely, because we want to preserve the integrity of that WTCM forecast above 34 knots. Again, when we are determining feature location, we go about this depending on whether or not we have the presence of WTCM. So when WTCM is present, we use the center that we find with the WTCM forecast. It is whatever we find, that is where we place it back on to that background grid. But when WTCM is not present, hybrid features are again placed at a mean center location of all inputs. We currently have an equal weight set between those, HMON and HWRF models, but we can weight those if we feel like one needs to be given a heavier weight over another. Now we can finish up our process with step 5 by placing the hybrids onto the background. We've made our hybrid feature and we're ready to place them onto our NVM wind speed background. So we'll go back to the Eric and Flossie case. Here we have the NVM 50% probability exceedance wind. This is on the oceanic domain. And so if you look at this, you can see where, it's okay. You can see where we might have a feature where Tropical Storm Flossie could be on that right-hand side, but definitely, very washed out broad winds there. And you can't really tell just by looking at it that there would be Tropical Storm Eric there on that left-hand side of that grid. So when we run feature match, we've seen, these hybrid features go through feature match and match together, and these are our hybrid feature masks. So this is where these two tropical storms are supposed to be and what they look like as a hybrid feature with their masks. So we can place these hybrid features back onto the grid, and this is what this combined forecast looks like. It definitely denotes two meteorological features, and definitely a lot more information here than there was a couple slides ago without a feature matched result. Here's a summary of what we just showed with the background winds at the top left side, with HMON and HWRF just below that, the inputs that we were working with, the HMON and HWRF wind speeds and feature masks. And on the right hand side, for me, it's really cool to see just compared side by side that 50% probability exceedance value with that combined forecast and how much of a difference it makes when you feature match and place these back onto the background grid. And then the hybrid feature mask is below the combined forecast, just for reference of where those TCs go. So here's the tropical storm Eta case. Again, the oceanic mean wind speed on the CONUS NBM grid. You can't really tell that there's a tropical cyclone off the coast of Florida at all. So if you go over to the hybrid feature mask, you can see where we have that agreement, where that hybrid feature was lined up and resolved on that grid. And we place it back down onto that background grid. And now we have a full-fledged tropical storm Eta right where the WTCM depicts it to be. And here's again a summary of that with the NBM background on the left and the inputs below. All three of those inputs with their raw winds and the feature mass. And on the right hand side, the combined forecast with the hybrid feature mask below for reference. So this is we're revisiting that that animation that we saw earlier. How do we fare with diverging solutions between direct model output and the WTCM? Not very well. This is, like Geoff said, this is a pretty problematic forecast when you have those diverging solutions. So when you feature match them on the next slide, you can watch this cycle through maybe once or twice, that we no longer have a diverging solution, and that solution is resolved from NHC's WTCM is the solution, and you have that direct model output that follows along and is feature matched very well. So how do we fare in a multiple TC environment? This is from earlier this year, around September, when there were 5 tropical cyclones, 4 of which NHC was issuing advisories on, with 2 X's denoted as potential areas, which eventually did develop into tropical cyclones. So this was a fun test case because we ran feature matching on this date time cycle, and we returned 4 tropical cyclones. We returned results for Hurricane Sally and Paulette. I actually believe Sally was a tropical storm at that point. Tropical Storm Teddy and TD21, which I think turned into TS Vicky. And it's worth mentioning in the dotted line, tropical depression Remy, there was no longer any WTCM data for that because NHC had stopped issuing advisories. It had not been a tropical storm. So because WTCM was no longer making a forecast for that, it wasn't a feature in our WTCM, HWRF, and HMON feature matching. So we were able to correctly identify, I mean, you can still see where TD Rennie would be on that feature match grid. So it was really encouraging to see this result. Really, really cool. Hey, Geoff, are you on mute?
Yes, thank you. Thanks, Sam. So after running over the course of this pretty amazing 2020 Atlantic hurricane season, we've been pretty happy with what we've seen so far. The results have, for the most part, been really encouraging, and specifically, we've been pleased with the consistency of our matching algorithm and the visual presentation of the hybrid tropical cyclones. We've also gotten some positive feedback from our collaborators at NHC and AFS. We do plan on going back after the close of the season and evaluating more conclusively. That'll be kind of an interesting exercise to figure out the best metrics to use to do that. And also, I should note, we've highlighted some of our positive results here, but oddities can and do pop up sometimes. And when I say oddities, you may ask yourself, what can go wrong? And you can thank Dana Strong for that last one making its way in here. So feature matching forecasts can be found on the MDL whole story uncertainty and probability viewer, which at the URL listed there. You do need to know a login to get to that. Select NBM beta for the data set. Right now we're producing two kind of flavors of this guidance. One is the tropical speed, which is meant as an update to the NBM tropical wind speed field, which features the NBM background forecast, the HWRF, the HMON, and the WTCM guidance. We're currently producing that for CONUS, Hawaii, Puerto Rico, and oceanic domains, with Guam coming soon. And that's run 4 times daily at 1, 7, 13, and 19Z. And we're also creating a 10-meter wind speed for comparison that contains only the NBM background, the HWRF, and the HMON. That's available right now for CONUS, Hawaii, Puerto Rico, and Guam. Oceanic is coming for that, and that runs hourly. This is still a work in progress. We're making improvements as we evaluate over this unprecedented hurricane season. And as we see things, we're going in and seeing what exactly happened and making improvements. We are definitely looking at making some refinements to our matching logic, trying to take into consideration what's happening when some of the models are interacting with land and others aren't. We're looking at how we handle the time interpolation of our direct model output inputs in early lead time as we fill in between those 3-hour and 6-hour lead times. We do time interpolation on the DMO, and that can give us kind of an interesting caterpillar movement effect occasionally. We're working on speeding up our runtimes by spreading out the computational load and finding where we can leverage existing compiled libraries. We're also planning on adding U and V wind and wind gusts to our matching and hybrid calculating steps so that we'll be producing consistent fields for those. We plan to implement with National Blended Models version 4.1 in the second quarter of fiscal year 2023. In the meantime, forecasts will continue to be viewable on What's Up, and we intend to also make DRIB2 data available for download next season. As we wrap up, I just want to thank everyone who's helped support this work, the MDL, CIRA, and ACE Info Solutions team, Dave Rudak, our NBM lead, for his guidance, John Crockett with CIRA for his guidance and encouragement in making this VLab forum talk happen, our colleagues at NHC and AFS for their invaluable collaboration, as well as our international colleagues at the Canadian, US, UK Statistical Post-Processing Forum for their feedback and advice, the What's Up team for making it so much easier to evaluate and share our forecasts, and also our colleagues at MDL Statistical Modeling Division for their enthusiasm and some very lively tropical discussions as we shared our work. And of course, thank you to all of you for joining us. I think we can open it up for questions or comments, but also if you want to take it offline, I've listed our email addresses down below and you can email us directly.
All right, thank you, Geoff and Samantha. Very, very interesting talk. Stimulates lots of thoughts and so forth. And so we're now in our question and answer session. So if you have a question, please use the raise your hand feature in the GoToWebinar to raise your hand, and John Chattel can unmute you, or type your question in the chat feature and we can relay that question to our speakers directly, or actually just relay it to them. But I'm going to start off with a couple of questions myself. So just a technical thing on the WhatsApp viewer NOAA login. It's a CAC enabled, right? So if you have a CAC card, they'll get you in, right? Yes. Okay, nodding yes. So you don't need a special password. You just need your CAC card. All right.
It's a CAC card, and if you like deny it enough times, you can just put in your email and password. Your just regular email credentials. It'll let you in that way too.
Okay, so now onto this what you described, this process is done at every projection in the blend, right? So you have to go through this every single time there is a explicit forecast, right?
Yes. So we run this for each of about 50 lead times for every cycle that we run, and then for each of the domains that we run.
So does that translate into some uncertainty in the actual running of the blend? Because if you have, like your last example, many features at once, can you add significantly to the computation time of the blend? It
can, although where we've found the biggest uncertainty in terms of computational time is we had introduced a function where we could remove background features from the base NBM forecast. We'd identify all the features on the NBM map and then remove the one nearest to the hybrid feature that we're placing. And as we got more into the shoulders of the tropical season, we were finding that we were tracking down well over 300 background forecast features, which was really bogging down our computational time. So until we can find a way to make that more efficient, we've actually had to turn that function off.
Okay, and you used in your example, two models, the HWRF and the HMON, but do you use all of the models when you typically do this, or are you just using a subset of the models?
Right now, we're just using the tropical NWP, so the HWRF, the HMON, and then the guidance from the National Hurricane Center. Although we're not specifically tied to any set model, we can run with whatever we throw at it.
So, like, you're not using the European, for example?
Not beyond what's included in the background blend field, no.
Okay.
But we can always test with that.
So related to the number of models, tropical models anyway, in the UFS, the HWRF and the HMON are going away, and then there'll be the HAF. So does that mean you're now lacking a model to do this? I mean, in the future, of course.
Well, we would be largely combining that DMO with WTCM for the tropical, for our tropical products. And if you were looking at the standard 10-year wind speed, we would simply be more directly on the NBM grid. And one thing that I didn't get to in here is that by looking at the individual feature and not trying to average a whole grid or a whole nest onto our background grid, we can also eliminate some of the seams that you'll occasionally see show up in the NBM 4.0 tropical wind speed product that are the boundaries of of an actual computational nest for a model.
Okay, thanks. So, John, can we turn to the audience? Do we have any questions from the broader audience?
Sure. Pablo Santos has a question for us. I've unmuted him, and if you'd like to go ahead and ask his question.
I guess comment on question, right? Hey guys, great presentation. I know we talk about this in those biweekly course at times, and as we test on the WTCN here, but one of the thresholds, so you mentioned the threshold for each of the features that you identify, and then you use for WTCN threshold greater than essentially 34 knots. But we talked about this, especially when you're looking at applying this technique over land, because the WTCN we adjust the wing out of marine boundary layer to we bring it to the top of the boundary layer, then we adjust it down over land, driven by based on the underlying surface type, right? And the wind profile associated with that and the roughness parameters. So what that means is when a portion of the WTCM circulation is over land, you're going to have winds less than 34 knots, even within the radius of 34 knot winds. So I'm wondering, you can comment on, how you are addressing that when you start looking at, this blending technique over land.
Well, that's a tricky consideration. That's a really good question. I think for the WTCM specifically, since we're never displacing the WTCM from its forecast location, that hasn't been as much of a problem, because where you see the reduced wind speeds in the TCM and where we place it on our map, it makes sense. It lines up with the correct, land type, the correct, terrain and elevation. It makes sense. Where you start to see it make less sense is if you've got an H-WRF and H-MON that we're now displacing from perhaps a different spot where they're interacting with land. And I think, we're looking at, Mark and Maria provided us with some information on that speed reduction algorithm that you guys use. And I think we're looking at perhaps coupling that with, a land water mask, land use data set. Mark also pointed us to that, as well as terrain elevation, to try to do at least some sort of reinflation, where we try to idealize, okay, what would this look like if it wasn't over land partially, and then combine them, and then kind of reduce it back down after we've placed it again. But that's just theoretical work right now. We haven't started down that road.
Okay, but right now you are preserving whatever the WTCM has, whether it's water or land, basically.
Yes, that's correct.
Then the second is just a question is of course, I saw your timeline, and I think Stefan, sort of alluded to this in one of his questions. In a real-time tropical scenario, I can tell you offices cannot wait soon enough for this. Okay, they simplify things. We also ingest the WTCM in the offices. We have a way to put it on top of the blend currently until this is out there fully operational. But the question is, what, based on the runtime you're seeing now, because you go into an advisory cycle every 6 hours, and normally we need to have the winds done, 30 minutes, 50 minutes before advisory time. Using that latest forecast from NHC that is going out with that advisory, the WTCM runs in less than 5 minutes, and we push it directly to the WFO, so they have it. But how long does the process of inserting that, following this technique into the NBN, is currently taking? Because we need to talk eventually down the road about that timeline. Is it going to be operationally available in a feasible timeline that fits the operational need? I guess that's where I'm coming from.
Well, that's something that we're striving for. Right now, the standard that we're trying to hold to is matching the current delivery time of the NBM tropical wind speed product. And I know you guys have done a lot of coordination to try to get that as good as possible. But some of these improvements in speed that we're looking to do, splitting up some of the computational load by identifying features as our model data come in, looking where we can leverage compiled routines that'll be a bit quicker than our interpreted Python script right now. We're looking to find whatever speed we can, where we can find it, so that we can provide this with as little delay as possible.
All right. Okay, well, thanks.
Thank you.
Thank you, Pablo. Other questions? John?
Yes, we have Frank Alsheimer has asked through the question pane, on slide 52, you talk about the tropical winds run at 01Z and 07Z, etc. Are those using the National Hurricane Center forecast from 4 hours prior?
Oh, that's a great question. So they are using, it's about 1 hour old data. So we try to run as fast as we can as soon as the data is there. But so if you're looking at a 1Z tropical speed product, we are taking the 0Z TCM product. Also, we're taking the 1Z NBM background, unless it's tropical, in which case we're taking the 0Z, or else it's oceanic domain, excuse me, in which case we're taking 0Z. And then it's the tropical NWP that's actually more delayed. We're actually going to be pulling that from the previous day's 18Z cycle. So we're always grabbing the most current most current NHC product available, usually about an hour prior to our initialization time.
And I've just unmuted Frank if you wanted to ask any follow-up.
Yeah, I'm a little curious about the WTCM. You said 0Z, because the WTCM product we get is actually like 21Z and 3Z. It's not 0Z. That's really what prompted the question. It's really sort of similar, honestly, to what's already been asked, is that when I see this slide, I think, well, that's nice, but in an operational setting, we're never going to be able to actually use it for our forecast.
Okay, so this mirrors what's currently input into the current Blend 4.0 tropical wind speed. I believe we grab a preliminary grid from, I believe the data we get is labeled as like a 0Z initialization, for example. And we do delay a little bit. So we label our cycle runs at 1Z, but we do bake in, I think, about an hour delay to wait to make sure that we can get that preliminary WTCM product. Does that kind of answer your question?
No, I'm still a little, I think what you're seeing as a TCM product is different than what we think of as a TCM type of product. And so I think there's a language barrier there that's going to make it difficult to answer this question in a short period of time like this.
Okay, so maybe Geoff, and you can work with Frank offline to kind of resolve this. And if we have a clarification, John Chittel can post it to the VLab form list so everybody can get it. I had a follow-up question on maybe taking this and applying it differently, this technique. So first question is, could we do the same thing with extratropical cyclones? And what would that mean?
I think absolutely. These feature-based approaches, or object-based approaches, are very good for looking at areas of high impact, high magnitude weather. Anything that you can, pretty easily identify with the transformation into a binary field, you can do that. You can take an extratropical system and match it across. Now, because we're running right now on tropical NWP, that only runs under certain conditions and tends to, very heavily feature the tropical cyclones, we're able to make some assumptions that allow us to be a little bit less stringent in our logic. So I think that we'd have to really take a fine-tooth comb to things like our matching algorithm and really refine thresholds and criteria to do it. But I think we could apply this to any number of high-impact weather events.
Okay, applied R&D to come. And a follow-up is like flipping the whole thing around. I know what you're trying to do, but the opposite, which is the direct model output, seems to me of a different interest potentially, in that divergent solutions, that's information about the uncertainty that could very well be very useful in a IDSS context. So basically taking that and saying, here's where different models are showing the evolution of this storm. So have you looked at it in that way as another product or a companion product?
Well, I would like to, is my answer. It's something that I've thought of. I've looked at the idea of running this matching across lead times for an individual model and being able to create kind of a plot to show the diverging solutions, sort of our own spaghetti plot, but more of an impact-based spaghetti plot. I think there's a lot we could do there. Right now, our tasking has been primarily focused on getting this kind of version 1.0 deterministic version of what we're doing out there. But absolutely, because we're identifying the features and retaining all this data about them, where they are, what their magnitudes are, it's all under the hood, and we have access to that. And it's just kind of figuring out what that's going to look like, what the end product that we're looking to create should be.
Very good. John, do we have other questions?
Yes, Brian Moretsky wanted to contribute to the discussion about product timing. Go ahead, Brian.
Can you hear me?
Yes, go ahead.
Okay. Yes, it is confusing in terms of the timing. So it is not an easily explainable item. We should follow up, and it's nobody's fault. What we can do is we can follow up and provide some more details on the timing, but suffice to say, as what we are doing, I think is what Geoff, you addended to, was that we are using the latest TCM information from NHC, and Pablo, if he's on, or others can try to clarify, but we are using the latest information that is available, and I thought it was the pre-TCM, and that's what we are using to go into the forecast. Now, we do caveat mTOR, we do realize that the timelines still don't necessarily match up with the WFO population timelines. So even though it is available from the NBM, it's still not matching up exactly with the WFO population timelines to get their wind forecasts out based on the latest NHC advisory. That is something we are working on as in sort of a companion but separate effort to what Geoff and Samantha are doing, just to make sure that the feature matching is working correctly and getting that spun up and stuff like that. The timing aspect is also something that is being looked into.
And Pablo, did you want to add anything? I saw you put a comment in the question.
Yeah, that's Brian read my mind, and he's playing better what my question was at first. But in the context of that example, you consider a 3C advisory, which is based on 00C motorcycle, like the Tropical NWP, right? That you guys are using for the background. The actual preliminary WTCN that will match the 3C cycle that will be based on the 3C forecast from NSC will be available around 2-15Z. So the question is, can the NBN force run this technique on the latest NBN background, which presumably by that time will be the 1C one, right? With this latest WTCN such that WFO can use it with the 3C cycle and have a wind forecast that's commensurate with official forecast from NEC. And to me, that is, I think your technique is very promising. I think you're on the right track, but to me, the timing, the timeline, when is it available to the forecaster, that's the one thing that going forward, we need to keep very much in mind. But that's really what Frank is referring to. That's what I was referring to when I asked my question. We cannot have that be available 30 minutes after advisory time, because it will delay significantly when partners are expecting our products. So that's where we're coming from.
All right, thanks, Pablo, for that clarification. Very, that's the type of direct comments that we need to improve and take into account to make this an effective product for operations. John, other questions?
Yes, Joel Klein would like to know. He says, the process seems pretty labor intensive. How long does it take from beginning to end to do the 5 steps and produce results on the model? And then how often is that done?
Okay, so it takes right now, I think we're running just on our W Coast developmental queue, not really doing any parallel processing or anything. It's taking us, depending on the size of the domain, probably our largest domain is the oceanic domain, and that takes probably 20-25 minutes to run a single lead time. But the trick is that we run everything concurrently. We launch an individual process for each combination of domain and lead time. So in the end, it ends up being the time to run one single lead time is about, we finish everything else at the same time. So we're about 20-25 minutes, but we think we can do a lot better. especially if we're splitting up and running some of these pieces of it, saving out features, things like that, on model information as it becomes available, so that by the time that last piece, the TCM, comes in, we just run the identification on that, do our combination, and then we're done.
Okay.
And
Go ahead, Geoff.
I was just going to say, so we run this, again, we run 4 times a day for the tropical speed, and we run hourly for the 10 meter wind speed.
All right. Unfortunately, we're going to have to end a little bit early today, but I want to thank again our speakers, Geoff Wagner and Samantha Camposano, for really sharing this innovative technique. It's stimulated a lot of thoughts on a lot of ideas, which is the benefit both for on the science side and as well as the operations side. And it looks like, you know, you got a cheering audience. Can't wait to get this. That's a good thing. So good, excellent work. Thank you both. And if you want to have follow-up questions for either of the speakers or for Geoff Craven, please, there we go, shoot them an email and they'll definitely get back with you. So coming up in future talks, we have coming up shortly in December, another talk by Dr. Joe Rittberger and Jen Sprague. It's Risk and Uncertainty Communication using Probabilistic Information, an update. In January, in the new calendar year, we heard about the whole story uncertainty and probability viewer. We're going to hear about version 2.0. Dana Strom's going to present that. Speaking about tropical stuff, we have Brian Marashka, I guess is the name. He's going to give a talk about Florida summer pop climatology to supplement the blend, another MBM related talk. And in March, a first, we are going to have a space weather talk from Dr. Chris Balch of SWIFT-C. He's going to talk about the NOAA USGS 3D geoelectric field model, which I believe predicts, you know, the impacts on Earth, excuse me, from coronal mass ejection, the types of things that could fry our electric grid and so forth. So be marking your calendars for that very interesting talk in March. With that, I want to thank everybody for tuning in. And again, John will upload this talk to the VLab forum site shortly, and you'll get an email when that's up there. Thanks, everyone, and have a happy Thanksgiving.
You too, Steve.
Bye-bye.
Thanks, everyone. Bye.
Thank you.